I'm going to finish off this morning on geologic time and spend this part of the lecture on radiometric dating. We saw before how we can use relative dating to rank the geologic events in terms of occurrence without actually assigning ages. But radiometric dating lets us go further. We can actually give an absolute age of the geologic materials and events, usually in millions of years, by utilizing the radioactive isotopes of elements. Now, most atoms have a stable nucleus, protons and neutrons. However, a radioactive element is different. It has an unstable nucleus. And over time, the unstable nucleus decays to a more stable form, and in the process becomes an entirely new element. So the idea behind radioactive decay is that we start out with a parent isotope, which is the original unstable radioactive isotope. And over the course of time, the parent will spontaneously decay into a new, more stable isotope referred as the daughter, and in the process result in the formation of an entirely different stable isotope. And the idea is that over time, unstable parent isotopes decay to more stable daughter isotopes at a rate measured in terms of half-lives. And we'll take a look at this idea of half-lives in a little bit more detail. But first of all, let's just go over the three principal types of radioactive decay, which include alpha emission, beta emission, and electron capture. Now, alpha emission results in the loss of 2 protons and 2 neutrons in what's known as an alpha particle. And as a result, the overall decay results in a stable daughter isotopes where the atomic number has decreased by 2 and the atomic mass decreased by 4. Recall that the atomic number is the number of protons within the nucleus, so with the removal of the alpha particle, the daughter nucleus contains 2 fewer protons. Alpha particle also includes 2 neutrons, so we have a total decrease in mass by 4. And the resulting daughter nucleus is an entirely new element from the original parent because of the change in the number of protons. Now, in the case of beta emission changes a neutron into a proton. And this results from the emission of a beta particle, which is basically just an electron. If we start out to the left with the original parent isotopes, notice that one of the neutrons can be represented by both a positive and a negative charge. The idea is that the 2 charges cancel one another. But with the emission of a beta particle, an electron, the neutron is then left with only a positive charge, and in this way the neutron converts into a proton. So in the process of a beta emission, the atomic number of the daughter increases by 1, whereas there's no change in the atomic mass because we're simply replacing a neutron with a proton. Electron capture in turn changes a proton into a neutron. Beginning again with the unstable parent nucleus, notice that we start out with a proton that has a positive charge indicated. And when this proton captures an electron, we end up with a particle that has both a positive and a negative charge in the daughter element. And by definition, the proton then changes into a neutron. And so in electron capture, the atomic number decreases by 1, but we do not get a change in the atomic mass because we're simply substituting a neutron for a proton. But again, the daughter nucleus is an entirely new element relative to the original parent. Okay, does everybody see this? Now, uranium-238 decays to a series of intermediate daughter isotopes, but those daughter isotopes are also unstable and continue to undergo radioactive decay until eventually, at the very end, we get the ultimate stable daughter isotope, lead-206. So, for example, here we can see the decay of uranium-238 in coordinates of atomic number on the horizontal scale and atomic mass on the vertical scale. So starting out with uranium-238 at the top, this isotope has 92 protons. So its atomic number is 92, and its overall atomic mass is 238, and hence this assignment of 238 to the uranium. Now, the first thing that happens to uranium-238 is that it undergoes alpha emission to become thorium-234. Notice that thorium has an atomic mass that's 4 fewer than the original uranium-238, and what's more, its atomic number decreased by 2. This is just a consequence of emission of an alpha particle. On the other hand, this 234 thorium is still unstable and undergoes 2 beta emissions to become uranium-234. Uranium-234 undergoes a succession of alpha emissions in turn, eventually ending up as lead-214. Lead-214 is still unstable and undergoes a couple of beta emissions to become polonium-214. Polonium, in turn, kicks out an alpha particle to become lead-210. Lead-210 undergoes 2 beta emissions to become polonium-210. The final step is polonium undergoing alpha emissions to become lead-206. Now, once lead-206 forms, that's the ultimate stable daughter isotope, and at that point, no further radioactive decay occurs. Pardon? Those we'll look at that when we look into half-lives. But a half-life, by definition, is the time required for half the number of initial paired radioactive nuclei in a sample to decay to the stable daughter isotopes. And so we see in this particular illustration, if we start out with 100% parent isotopes, after each half-life, half of the initial parent isotopes have decayed to daughter isotopes. So let's start out, for example, with an initial magma that has a mixture of radioactive and stable atoms. So this is the magma, and within the magma, some of these atoms are stable. The stable atoms are indicated by the light blue spheres. And we also have radioactive atoms that are indicated by the dark blue spheres. Now, over time, as the magma cools and eventually the earliest minerals are going to crystallize from the magma chamber. And notice that the early crystallized minerals are only incorporating the radioactive element, radioactive isotope of the element, but not the stable atoms. So each one of these newly formed crystals starts out with 100% radioactive parent. Okay. Now, the reason the early crystals are incorporating only the radioactive atoms is because it's those atoms that fit nicely into the crystal structure. Now, over time, eventually the magma will completely crystallize to an igneous rock. And afterwards, as time passes, the radioactive atoms that were initially incorporated into those early crystals will then undergo radioactive decay to daughter isotopes. So that after one half-life, notice that within these crystals, half of the original radioactive parent has decayed to stable daughter isotopes. Does everybody see this? Okay. Now the time that it takes for half the parent isotopes to decay to daughter depends on the parent-daughter pair that we're looking at. It differs for different parent-daughter isotopes. So let's look at this again in the graph of percentage of radioactive isotopes remaining in the vertical scale versus the number of half-lives in the horizontal scale. And let's start out at the top where we start out with a crystal or a mineral with 100 atoms of parent isotopes. And this occurs during the initial crystallization from the magma. And afterwards, the magma completely crystallizes into an igneous rock. And over time, the original parent isotopes in the crystals will start to undergo radioactive decay to more stable daughter isotopes, such that after one half-life, notice that the crystal now contains 50 atoms of parent and 50 atoms of daughter. Okay? What's going to happen after the next half-life? After two half-lives, we're down to 25 atoms of parent and 75 atoms of daughter. Notice that during the time span from 1 to 2 half-lives, the parent isotopes that were present after one half-life, half of those parent isotopes have decayed to daughter isotopes, so that the proportion after two half-lives is 25 atoms of parent and 75 atoms of daughter. After 3 half-lives, or after 4 half-lives, we're down to 6 atoms of parent and 94 atoms of daughter. Notice that in each case, when we take the sum of the parent plus the sum of the daughter isotopes in the crystal, we end up with 100 atoms, the same number of atoms we started out with. Okay? Any questions on this? Now, the commonly used parent-daughter isotopes in radiometric dating of geologic materials are indicated in this table. We saw before that uranium-238 will decay to stable daughter lead-206. We saw previously that there are a series of intermediate daughter isotopes that are produced in the scheme, but those daughter isotopes further decay further down the sequence, but ultimately we end up with lead-206. Now the half-life in going from uranium-238 to lead-206 is 4.5 billion years. For uranium-235 that decays to lead-207, the half-life is 704 million years. For thorium-232 to decay to lead-208, it's 14 billion years, and so on and so on. The point is that the half-life for the parent to decay to daughter varies depending upon which parent-daughter radioactive isotopes we're looking at. You don't have to memorize these. These are just examples of different half-lives for different parent-daughter isotope pairs. Okay, yeah. The half-lives are actually measured in the laboratory. They take samples that have high concentrations of parent and just measure the rate of decay of those parents. And then you can use equations to calculate the half-life. But it's done in experimentally. They take a high constant, they take a lot of parent isotopes and just measure the rate of decay. Now, they don't necessarily have to measure it all the way down to one half-life, but they can measure the rate at which the parent isotope decays to daughter, that they can use equations to calculate the actual half-life. Obviously, they're not going to sit around, they're not going to start out with 100% uranium-238 and wait 4.5 billion years for half of those to decay. They measure the rate at which the uranium-238 decays, and they can calculate the actual half-life from that.
The time scale is billions of years, so how long?
Now, for radiometric dating, we need to know two things. First of all, we need to know the half-life of the isotope being measured. And secondly, we need to know the parent-daughter ratio in the sample. And once we know these two things, the age of the sample can then be calculated. Now, we saw that the half-life can be determined in the laboratory, but what about knowing the parent-daughter ratio of the sample? Well, this is determined using an instrument known as a mass spectrometer. What happens is that the sample is prepared in a laboratory, the sample typically being rocks and minerals. And the sample is prepared to the point that it can be injected into a mass spectrometer as a liquid. And from there, a heater vaporizes the sample, and an electron source creates an electron beam which ionizes the sample. And from there, the ionized sample is propelled through the tube within the magnetic field. And the magnetic field will then separate the charged particles within the beam on the basis of mass. In other words, the isotopes can be separated within the chamber. And from there, at the very end, there's a detector to measure the ratio of the different isotopes within the sample. And that's how the parent-daughter ratio is determined. So let's take an example. What is the age of a sample if the ratio of radioactive parent to stable daughter has been measured and found to be 1:1, and we know that the half-life is 5 million years? What would be the age of the sample? Yes. How do we get that? Well, the ratio of parent to daughter gives us the number of half-lives that have passed. Notice that if the ratio of parent to daughter is 1:1, the only time you're going to have that ratio or proportion is after one half-life, where we have 50% parent or 50% daughter. So we know that one half-life must have passed if the ratio is 1:1. And since we know that the half-life is 5 million years, the sample must be 5 million years old. What about if the measured proportion of parent to daughter was 25% parent and 75% daughter? What would be the age of the sample? Yeah, if we found in the sample that there was 25, if the ratio of parent to daughter was 25% parent and 75% daughter.
Then there's 2 half-lives, so it's 10 million years.
Yeah. 25% parent, 75% daughter. The only time you get that proportion is after 2 half-lives. And if 1 half-life is 5 million years, 2 half-life is 10 million years. So the sample would be 10 million years old. After 3 half-lives, the sample would be 15 million years old. After 4 half-lives, 20 million years, and so on and so on. And so that's how we use the proportion of measured parent-daughter ratios to calculate the age. And this is done using equations. So is there any question? So if I was to give you a question like, for example, if the ratio of parent to daughter was, say, 12.5% parent and the rest being daughter, what would be the age of the sample if the half-life was given? And you should be able to calculate the half-life, or the age of the sample. Now, in actuality, you're not going to have really nice proportions of 1 to 2 or 1 to 3 for parent isotopes. Usually what's measured in the mass spectrometer is a value like 0.006325 for the parent-daughter ratio. But even so, you can plug that number into an equation and calculate an age. Now, to make things a little more complicated, isotopic ages can be reset by metamorphic event. If we think of these as isotopic clocks that are ticking along as more parent isotopes are decaying to daughter isotopes, a metamorphic event coupled with an increase in temperature, if the temperature becomes high enough, the daughter isotopes can actually escape the minerals where they accumulated, and at that point the isotopic clock, in this case the minerals, are reset back to 0 in the process. Let's say that 1,000 million years ago there was a magma that crystallized a mineral starting out with 100% parent isotopes, as indicated by the black dots in this figure. Now, the magma eventually completely crystallizes to an igneous rock. The rock cools, and as time passes, the parent isotopes are going to decay to daughter isotopes within the crystal. And let's say the half-life is 500 million years. After 500 million years, we see that we have 50% parent and 50% daughter within the mineral. Okay? But then, soon afterwards, say about 480 million years ago, there's a metamorphic event, and the temperature of the rock is raised to the point that the daughter isotopes escape the mineral into the surrounding rock matrix. At this point, we have reset the isotopic clock. The mineral now only has 100% parent isotopes in the crystal. Okay? The daughter isotopes have escaped into the surrounding rock matrix. Now, the reason this occurs is that if we start out in the crystal structure, when the mineral first formed, the parent isotopes fit nice and snug into the crystal structure. But then when the parent isotope decays to a daughter isotope, the daughter isotope no longer fits very well into that crystal matrix. It kind of wobbles around, so that when the temperature is raised and the atoms are excited, that loosely fitting daughter isotope is not retained in the crystal structure and escapes into the surrounding matrix. Whereas the parent isotopes are still nice and snug and remain within the crystal. And that's why the isotopic clock is reset. Now, after the metamorphic event, the rock again cools, and then as time passes, the remaining parent isotopes will start to decay to daughter isotopes, so that about 500 million years afterwards, or today, we're back to 50% parent and 50% daughter in the crystal. Now, if we were to remove this mineral and measure the parent-daughter ratio, what age would we get from that mineral? What would be the mineral age? Yeah, the mineral would give the age of the last metamorphic event. On the other hand, if we took the entire rock and crushed it into a powder and analyzed that powder, what would be, we would not only be counting the daughter isotopes within the crystal, we would also be counting the daughter isotopes within the rock matrix. What would the whole rock age there then reflect? Yeah, the whole rock would give us the age of the initial crystallization, because we're not only counting the daughter isotopes in the crystal, but also the daughter isotopes within the matrix. Well, the point here is that in metamorphic rocks, the mineral ages can determine the age of the last metamorphic event, whereas the whole rock age will give us the age of initial crystallization. So we have two different ages, and both of these ages are very important to geologists.
Say, for example, we have that nice rock, and that's a metamorphic rock, right? So
Mhm.
it's got, it's got feldspar, it's got,
Yeah, we could measure the age of the feldspar in the metamorphic gneiss. We can measure the age of the biotite minerals. Typically, we can have zircons. Maybe we can determine ages on the zircon minerals, and each of those will give us a mineral age. And if the calculation, if all goes well, those mineral ages should more or less agree with one another, and give us the age of the last metamorphic event.
so then how do we use that nice rock to get the age before the metamorphic event?
The crystallization age, if we just crushed the rock and we took the, if we crushed the metamorphic rock, and then we would not, the resulting sample would not only include daughter isotopes from the crystals, it would also include the daughter isotopes within the surrounding rock matrix. And that should give us the age of the initial crystallization.
Would the sample be enough, or would it be?
Now, a carbon-14 dating is typically not performed by geologists, but it's useful just to see what's the basis for carbon-14 dating. And we start out in the atmosphere, where we have these cosmic rays entering the atmosphere, shattering gas atoms and releasing neutrons in the process. From there, some of these neutrons are absorbed by nitrogen atoms within the atmosphere, And when these neutrons are absorbed, the nitrogen kicks out a proton and in this way converts into 14 carbon. And this is the general process. Here we have nitrogen 14 capturing a neutron, kicking out a proton, and in the process, nitrogen 14 is converted into carbon 14. Now from there, the carbon 14 combines with oxygen in the atmosphere to form CO2. From there, living matter absorbs the CO2, some of which contains 14 carbon. Now, the absorbed 14 carbon is unstable and will eventually decay back to 14 nitrogen with a half-life of a little over 5,000 years. And it does so through beta emission. So you see in this figure that carbon-14, one of the neutrons will kick out a beta particle and convert to a proton. And in this way, carbon-14 changes back into nitrogen 14. This is a very short half-life, 5,730 years. Now, during life, whether we're looking at plants or animals or even water, the 12-14 carbon ratio in living matter or water is constant, remains constant, since any decaying 14 carbon is continually being replaced by new 14 carbon from the atmosphere. 12 carbon is stable and does not decay. After death, however, the 14 carbon in the organism continues to decay, but is no longer being replaced by 14 carbon from the atmosphere. And as a result, over time, the 12 to 14 carbon ratio in organic matter following death will gradually increase over time as more 14 carbon disintegrates. And this is the basis behind 14 carbon dating. Basically, the 12 to 14 carbon ratio is measured in organic material, whether it's bone or shell or in oil within paintings, charcoal within archaeological sites. This is the basis for assigning an age to those materials. The problem is that 14 carbon dating is only useful for carbon-bearing materials younger than about 80,000 years. What happens in material that is older than 80,000 years? Why can't we use this method anymore? After 80,000 years, there's just hardly any 14 carbon left. So once all the 14 carbon decays, you can no longer get a ratio of 12 to 14 carbon, and so at that point you can't date the material. You have to have some parent isotope remaining in the material in order to get a parent-daughter ratio, and that's why. That is why geologists use parent-daughter ratios with very long half-lives, half-lives of hundreds of millions to billions of years, because when geologists date rocks and minerals that are very old, like maybe hundreds of millions to billions of years, you still have to have some parent isotope in the sample in order to get an age. Okay? So in summary, igneous rocks can provide an approximate crystallization age using whole rock analysis. Minerals also provide a crystallization age, provided that the rock has not experienced subsequent metamorphism. In this case, the mineral age should agree with the whole rock age. But we saw that metamorphism will reset the ages of minerals. Minerals in the metamorphic rock can provide an age for the last metamorphic event. If the rock, however, experienced more than one episode of metamorphism, then usually only the most recent event can be dated. With each metamorphic event, the isotopic age of the minerals are reset back to zero. Okay. On the other hand, in the case of sedimentary rocks, clastic sedimentary rocks do not give meaningful ages because the minerals contained within these rocks were derived from other sources or from multiple parent rocks. Clastic minerals in detrital sedimentary rocks only provide the ages of their parent source rocks, and these ages do not reflect the time of sedimentation. Another problem is that multiple parent rocks of different ages contribute sediment to the same basin, and this mixture of different ages in the basin ends up being meaningless if you're trying to date the time of sedimentation and formation of, say, a sandstone or a shale. Here, for an example, we see sedimentation within the Gulf of Mexico basin. And notice that the sediments are coming in from multiple source rocks located in vastly different areas. So the question becomes, when did sedimentation occur? How do we answer that? We don't know because the mineral ages only reflect those of the source rocks. However, if we look at soft fossils within sedimentary rocks collected within the Gulf Coast basin, the fossils can be used to date these different sediments. And this is what paleontologists and oil companies do. They, in particular, they look at microfossils from, say, foraminifera in order to determine the ages of each of these different sedimentary rock units. Now, here's an interesting case, however, where the mineral age can provide important information within a sedimentary rock. As an example, in Western Australia, there's a location called the Jack Hills, where we find meta-sandstone, meta-sedimentary rocks that give an age of about 3.5 billion years old. Now, the detrital zircons that were recovered from the 3.5 billion year old Jack Hills meta-sandstone at this location are much older than their meta-sandstone host. So the interpretation is that the zircons may have originated from earlier granites that no longer exist and subsequently were incorporated within these meta-sandstones. The ages of these zircons range anywhere from about 4 billion years all the way back to 4.4 billion years ago. This vertical bar, color-coded lavender, gives the range of ages of these oldest zircons that have not only been found in Australia, but also in places like Canada and Greenland, where many of these ancient Precambrian rocks are found. Now, if we take the age of the oldest zircons that have been found to date, about 4.4 billion years ago, this is an estimate of the oldest continental crust on Earth. Unfortunately, we do not find relics of this continental crust. It's long gone, but the presence of these zircons tells us that this crust once existed. And this is a good example of how we can use these individual minerals within sedimentary rocks to get information about a time period in the distant geologic past that no longer yield whole rock information. Isotopic dating of a sedimentary rock is possible if it contains authigenic minerals or other materials such as glauconite, potassium feldspar, or organic matter that formed during actual burial and diagenesis within the sedimentary basin. For example, during burial within the basin, new minerals can precipitate within the sediments. Minerals like clays, for example, kaolinite, and other minerals. And these authigenic minerals, when dated, can provide an age of diagenesis within the basin itself. And in this case, we can date the time of formation of the sedimentary rocks. On the other hand, if the minerals were brought in from other sources like parent rocks, those ages are not very useful. We can, however, bracket the age of sedimentary rocks. For example, if we can date underlying and overlying igneous and metamorphic rocks, or, for example, interlayer volcanic ash deposits cross-cutting igneous dikes, these are materials that can actually be directly dated. We can apply the principles of relative dating and kind of bracket the age of the resulting sedimentary sequences. Here, for an example, within a region of western North America, where we have a series of sedimentary rocks like the Dakota Sandstone, the Manco Shale, the Morrison Formation. There are two materials we can date within this sequence. One is this igneous dike, which has been dated at 66 million years. Another is a volcanic ash bed that's been dated at 160 million years. The assumption is that volcanic ash bed was deposited on the surface prior to deposition of the overlying sedimentary units. Now, by dating these two igneous units, what can we say about the age of the Dakota Sandstone? Yes, we can apply the principles of relative dating. For example, the Dakota Sandstone occurs above the volcanic ash, and so the sandstone must be younger than 160 million years. On the other hand, the Dakota Sandstone is cut by this igneous dike dated at 66 million years, so the sandstone must be older than 66 million years. And so, see, we've essentially bracketed the Dakota Sandstone so that we can say that this sandstone has an age somewhere between 160 million and 66 million years. What about the Wasatch Formation? What can we say about the age of this unit? We can be even more precise. It's actually not between 160 or 160 and 66. Notice that the dike does not cut the Wasatch Formation. So what can we say about its age? It's younger than 66. Yeah. The Wasatch was deposited after emplacement of that igneous dike. So the Wasatch Formation has to be younger than the dike. And that's what's meant by bracketing the ages of sedimentary rocks. Now, if these rocks contained fossils, and we knew the age of the fossils, we could even better constrain the ages. But in this case, we're just looking at two dated igneous materials. So in summary, dating with radioactivity, radiometric dating is a complex procedure that requires precise measurement. Rocks at several localities have been dated at more than 3 billion years old, and this in turn confirms the idea that geologic time is immense. And as a result, geologists have been able to construct what's known as the geologic time scale, or basically a calendar of Earth history. The time scale subdivides geologic history into units and was originally created using relative dating. Absolute datings were assigned later after the discovery of radioactive activity back in 1896. Now we see that the geologic time scale is subdivided into various units of time. The largest divisions are eons, which include the Phanerozoic and Precambrian. Eons, in turn, are subdivided into eras. Eras are subdivided into periods, and periods are subdivided into epochs that constitute the smallest divisions. So eons, which are the largest subdivisions or divisions, can be subdivided into Hadean, which is the oldest, ranging from the age of the Earth, 4,600 million years, to 4,000 million years ago. The Archean eon ranges from 4,000 to 2,500 million years ago. The Proterozoic from 2,500 to 541 million years ago. And then the most recent eon, the Phanerozoic, began 541 million years ago and continues to the present. Eons are subdivided into eras, and the eras of the Phanerozoic include the Cenozoic, the Mesozoic, and the Paleozoic. Eras, in turn, are subdivided into periods. Periods are subdivided into epochs. And in all cases, notice that the time divisions are in millions of years. And what's more, the geologic time scale can be tied into rock units or formations. So that, for example, the Umpire group of the Grand Canyon is assigned to the Precambrian. The Supai group includes the Pennsylvanian and part of the Lower Permian period. Hermit Shale corresponds to the Permian period, and so on, etc., etc., etc. And here's the evolution of life over the last 4.5 billion years, but we're not going to go into too much detail with this. This will pretty much end this particular lecture.